Welcome to episode 27 of 100 Days of Data. I'm Jonas, an AI professor, here to explore the foundations of data and AI with you.
And I, Amy, an AI consultant, excited to bring these concepts to life with stories and practical insights. Glad you're joining us.
Inspired by the brain running on silicon. That's a simple way to think about neural networks, the building blocks behind much of today's AI.
Yeah, it's amazing how something inspired by biology now powers everything from your phone's voice assistants to personalized shopping recommendations. So let's dive in. What exactly are neural networks?
At their core, neural networks are a type of machine learning model designed to recognize patterns. They're loosely inspired by the human brain's network of neurons, hence the name. Imagine the brain, where billions of neurons send signals to one another. Neural networks mimic this by connecting units called artificial neurons, arranged in layers.
So these artificial neurons, they're not actual cells, right? They're more like tiny math functions that process information.
Exactly. Each artificial neuron receives input, does some simple calculations, and passes its output to the next layer of neurons. The network is organized into an input layer, one or more hidden layers, and an output layer.
And these layers are like stages in a factory line. Each step transforms the data a bit more until you get your final product, whether that's recognizing your face or predicting a customer's next buy.
Great analogy. Now, input neurons take raw data, like pixels of an image or sales figures. Hidden layers do the heavy lifting. They identify patterns and features by combining signals in different ways.
I've seen this in retail. A network might first spot simple features like edges in an image, then shapes, then entire objects as it moves through layers. In finance, neural nets comb through historical trends to detect fraud patterns that might be invisible to humans.
Each connection between neurons has a weight, a numerical value that adjusts during training. You can think of weights as the strength of the connections, like turning up or down the volume on certain signals.
And training means feeding the network loads of examples, like showing thousands of cat photos, so the system learns to distinguish cats from dogs.
Precisely. Through a process called backpropagation, the network tweaks these weights to improve its predictions gradually. It's like fine-tuning a radio to get the clearest signal.
Backpropagation sounds technical, but practically it's just trial and error on steroids. The AI guesses, checks if it's right or wrong, then adjusts itself to do better next time.
The magic lies not in any single neuron, but in how layers of them work together. They create complex, nonlinear functions capable of capturing intricate relationships in data, far beyond what simple models can handle.
That explains why neural networks are behind so many breakthroughs. Take healthcare. Convolutional neural networks, or CNNs, analyze medical images to detect diseases like cancer earlier than doctors alone.
Convolutional neural networks, or CNNs, are designed specifically for grid-like data, such as images. They use filters to scan parts of the image, much like how our visual cortex processes visual information in chunks.
I hope the hospital system adopts CNNs to flag anomalies in X-rays. Initially, doctors were skeptical, but the AI caught subtle details even seasoned radiologists missed. It didn't replace doctors, but acted as a powerful assistant.
Exactly. Neural networks excel as pattern detectors, but rely on human guidance for interpretation and decisions. Now, another popular type is the recurrent neural network, or RNN, which handles sequential data.
Those are great for things like speech recognition or financial time series. Basically, anything where order and context matter.
Right. RNNs keep track of previous inputs by maintaining an internal state, allowing them to model sequences over time. However, classic RNNs can struggle with long sequences, which led to improved versions like LSTM networks.
Long, short-term memory networks? I hear about them a lot. In real-world projects, they've helped with chatbots that remember conversation history and with forecasting inventory needs over weeks or months.
LSTMs overcome the forgetting problem by using gates that control how information flows through the network. It's a bit like deciding what to remember and what to ignore, very human-like.
I love how these concepts borrow from biology but adapt to computing constraints. But Jonas, neural networks can get pretty complex and opaque, right? That's often a tough sell in business.
That's true. Their complexity makes them what we call black boxes. They deliver great results, but don't always explain how. This opacity can be a challenge in regulated industries like finance or healthcare, where interpretability is critical.
I've encountered that firsthand. A bank we worked with wanted a fraud detection model, but also needed to explain decisions to regulators. We had to balance neural networks' accuracy with simpler, more interpretable models.
That's where hybrid approaches come in, combining the predictive power of neural networks with explainability techniques. Methods like SHAP values or LIME approximate which inputs influence decisions.
I've seen those tools in action. They generate visual explanations showing why the AI flagged a transaction. It builds trust, even if the full network remains a bit of a mystery.
Another practical consideration is data. Neural networks require large amounts to train effectively. The more complex the network, the more data it needs, or it risks overfitting, memorizing training data without generalizing well.
Which is why companies with rich data assets like big tech firms or banks often lead in neural network applications. But smaller businesses can still benefit through transfer learning, using pre-trained models fine-tuned on their own data with less effort and data.
Exactly. Transfer learning lets you leverage knowledge embedded in a network trained on enormous datasets, then adapt it to your niche problem with less effort and data.
For example, I helped a manufacturing client use a pre-trained image recognition model to spot defects on assembly lines without building a neural network from scratch. It gave them quick, cost-effective results.
To summarize, neural networks are powerful AI models inspired by our brain structure. They use layers of interconnected artificial neurons, adjusting weights to learn from data.
They shine in tasks involving images, speech, language, and complex patterns, enabling real-world impacts across industries, from personalized marketing to medical diagnosis.
The key strengths are their ability to model nonlinear relationships and learn hierarchical features automatically.
And the challenges include their need for large data, computational resources, and explaining their decisions in transparent ways.
Key takeaway? Understanding the basics of neurons, layers, and weights helps you see how neural networks capture complexity in data that traditional models can't.
And from a business standpoint, knowing their strengths and limits prepares you to ask the right questions and leverage their power strategically.
Next time, we'll explore natural language processing, how AI understands and generates human language, making chatbots and translators possible.
If you're enjoying this, please like or rate us 5 stars in your podcast app. We'd love to hear your comments or questions. We might feature them in future episodes.
Until tomorrow, stay curious, stay data-driven.